Hi all, this is weird, I was talking about the live stream and people here in our office in Martinson Mayor's office in Dublin. This is our October, our August live stream for Rust. So I'm just going to introduce you to Luciano, who's talked to us before. Many thanks to him for presenting again this month. So this is Rust, serverless in AWS. There you go. And that's it, no further ado. Luciano, here you go.
All right. Thank you very much, Alan. So I'm gonna start very quickly, but before I introduce myself, just quick thing. I have the slides already online, so if you want to grab the slides, just scan the QR code or get the link. Or if you're watching the recording on YouTube in the future, you probably find this link in the description. And this is because I have a bunch of code examples, so maybe you want to review them later, so it's good to have the slides. So, who am I? Hello everyone, I'm Luciano. As you can guess from the emoji, you probably understand my nationality from there. So, I am an AWS Serverless Hero and Certified Solution Architect. I work for a company called Fortheorem, and you might have seen my name if you are in the Node.js space because of this book. And if you have, let me know what you think. And I'm generally available online. You can find all my links there. So, if you want to continue the conversation later, just click there and connect on Twitter, LinkedIn, whatever you prefer. Okay, I'll tell you a little bit about Fortheorem. We are a consulting company specialized in AWS and serverless. These are some of the things we do: cloud migration, training, building high performance serverless applications, cutting cloud costs, and all this kind of interesting stuff. If you're interested either to work with us, because maybe your company needs this kind of help, there is an email there, but also we are always in hiring mode, so that can be interesting as well. Don't hesitate to reach out, and you can talk to me afterwards if you're interested. We also have a podcast for Fortheorem where we talk about all things AWS. There is a new episode every week, so check it out if you're interested in AWS. Okay, let's start to talk about serverless. So what do we do these days? If we don't know something, we ask ChatGPT. So I asked ChatGPT, what is serverless? And it gave me a very verbose answer. I'm not going to read all of that, but the summary is that basically it's a cloud computing model where the cloud provider manages the infrastructure and automatically allocates computing resources to execute code in response to events or requests. There are no servers to manage or provision. This is why it's called serverless. There are still servers somewhere, we just don't need to manage them. And developers only pay for the actual usage of their application, not for the infrastructure. So this was actually a pretty good summary, I think. But if we want to have a more simplified view, it's basically a way of running applications in the cloud. There are servers, as I said, you just don't have to think about them, and you only pay for what you use. One of the cool things is that you generally have to think it's small units of compute, which are called functions, and those are triggered by specific events. Now, why do I think that serverless is pretty cool? What I've seen in my experience is that you can generally focus a bit more on the business logic because you don't have to think about where is my server, how do I keep it live, how do I keep it up to date, how do we connect it to the network and all this kind of stuff. Generally, you think about functions, and what goes inside the function is mostly the business logic that you need to think about. And also because you're thinking in terms of functions, that kind of forces you to think in a smaller scales. By default, you don't really end up building monoliths, which makes it sometimes a little bit easier to work in a team where you can distribute different tasks and people can work a bit more in isolation. So you have less kind of everyone stepping into each other's toes. And there is some degree of automatic scalability. It's not magic as AWS would like you to think, but it can scale pretty well up to a certain point. I think if you really have a huge amount of traffic, you really need to understand what are the rules behind the scalability and make sure that those rules will work well for your specific use cases. But for most use cases, basically the idea is that if nobody's using your code, you are scaling to zero, there is nothing running. If you start to get lots of events and more users are using your service, then you will get more and more lambdas allocated for you and running, so it should scale up to a certain point. It's not a universal solution because it works well in many situations, but there are still use cases where Lambda is probably not the best solution, so just keep that in mind. Now, what is Lambda? we spoke about serverless, but specifically what is AWS Lambda? So serverless applies to all sorts of cloud providers. It's not a concept unique to AWS, but when it comes to AWS, Lambda is one of the main serverless services. Specifically, is the service that allows you to implement functions as a service. So the idea that you can write your code in the form of a function, and that function can be triggered by specific events. And just to give you an example, what is an event? It could be an HTTP request. It could be you are dropping a file into an S3 bucket, so that file can trigger an event and you can execute code as a reaction to that. It can be jobs that you have in a queue. It can be something that you are orchestrating like a workflow using a step function. And in that workflow, at some point you have some custom piece of logic, and that logic can be a Lambda function. Or maybe something you are running, I don't know, every Monday morning, maybe you need to scrape some information. So you have a schedule and you can trigger a function using that schedule. Finally, you can also invoke things manually. So you can create specific workflows, and only when you need them, you can trigger that Lambda manually. Now, just to give you a bit more concrete use cases, what can you do with HTTP? You can build an API combining API gateway and Lambda. You can build again a custom step function. I have an example later. You can process files in S3. For instance, you drop a video into S3, you extract 4 thumbnails and save them somewhere else. You can scrape and synchronize data on a schedule. One use case we had in the past, actually, when I was working with Alan, was we were downloading files for the electricity industry from an FTP and loading that data into a database, and we knew those files will appear every half an hour. So basically we had a schedule to connect to the FTP, get the new data, process it, and save it to our database. So these are just some of the examples that you can, just to think about what can you do with Lambda. Now, I said it's not magic. There are limitations, and it's important to understand the main limitations. The biggest one is that you cannot run an execution of a Lambda for more than 15 minutes. Then the payload size is limited, so the amount of data you can send in the request or that you can return in the response is limited. The limit is slightly different depending on the type of invocation, but the idea is that you cannot send more than a few megabytes. So that gives you an idea of the scale of data that you can receive or that you can return as a response. And you cannot have a GPU. So if you need to do anything that requires a GPU, you cannot use Lambda, at least to this day. So again, it's not a silver bullet. You can already imagine many use cases where you don't want to use Lambda. So Lambda is not a hammer for every problem. Some people would like to do that, but I still want to recommend to always try to figure out, is it a good use case for you? If it is, use it, it's great, but sometimes might not be the best option. Now, how do you pay for Lambda? Because we say that you only pay for what you use, but how much do we pay and what are the main dimensions? And there are actually 2 dimensions. One is allocated memory and one is time. And what does that mean? Let's try to understand it with an example. So basically, depending on how much memory you give to your Lambda function, and it's something that you have to decide up front when you provision the Lambda, you have a different price per millisecond. For instance, here I am, I think, looking at the Ireland region, EU West 1, and allocating 512 megabytes to this Lambda. And that means that I'm going to be paying this amount of $0.83 per millisecond. So something that looks like very low, but you have to remember that you have to multiply that for the number of milliseconds that you are executing your Lambda. So let's just say we are executing a Lambda for 15 minutes. This is what happens. So we end up paying $0.07. And now my images are not working anymore, which is great. So you lost the amazing joke there, but don't worry. Let's try to refresh.
You see.
Ooh. Now you see the joke. Terrible, but yeah, it was refusing to show the joke. Okay, so you might be wondering, is this 007 a lot or not? And I guess the answer is it really depends, right? Because if you're running this one-off, like once a week, it's basically for free because you don't even spend like $1, right?
Or even 1 cent.
Yeah, or even 1 cent, I guess. But if you're running this like thousands of times per minute, then you can start to do the maths and you can get to the point where you start to spend thousands of dollars per month very easily. So again, it's not necessarily the cheapest. It generally works really well if you have very spiky traffic, very unpredictable, because you are gonna kind of balance out compared to other solutions that are more, you allocate some compute, and that compute is gonna stay there until you shut it down manually, and you pay for the time that that compute is always available. I'm talking about like bare metal virtual machines, or I don't know, containers, things like that, where you might have a better price if you know exactly what is your compute and you have very constant rate of compute. But if it's very spiky, I think Lambda gives you a better price equation. But anyway, always try to do the maths, because it's always very hard to say in general this is cheaper or more expensive. Now, what about CPU? Because we only talked about memory and time. What if you need more or less CPU? Is that something that we need to worry about? Or if we want to worry about, because maybe we know for that specific task we need a certain amount of CPU, what is the kind of the idea there? And the idea is that you don't explicitly configure CPU. You will get more CPU the more memory you allocate to the Lambda. And there is a table, which actually is not an official table. AWS doesn't really give you an official table as far as I'm aware. But somebody did a test and tried a bunch of different combinations of memory. And basically they... Thank you. Microphone improvements. Hopefully the audio quality is better now. So you should be getting, as you see, the more you increase the memory, the more virtual CPUs you get. So the idea is that if you need more CPUs, you allocate more memory, which means you end up paying more. Okay, what's the execution model? So we said it's serverless, so it should run only when needed. The Lambda code is generally stored in S3, and we said that it is event-based. So at some point there might be an event that requires AWS to run your own Lambda. So what's the idea? If there is no instance of that Lambda available, because we need to allocate some compute resources somewhere, at the end of the day, Lambda is just a micro VM, so we need to spin up that micro VM somewhere. So what happens is when the event happens, AWS is going to check inside the Lambda runtime, do we already have an instance running for this particular event? If no, we need to create one, or AWS needs to create one. And what happens is that basically they will download the code from S3, and they will spin up this virtual machine and run this function that can manage this event. And because this takes a little bit of time, this is called a cold start. So the first time we are spinning up a new instance, we have to pay a little bit of extra price just for the whole infrastructure to be provisioned. But if an instance is available already, we are not going to have to pay that cost again, because we can just redirect that event to that instance. And basically AWS is going to keep the instance around for a while, just in case that some new events are going to come in. Of course, if no events are going to come in for a certain amount of time, let's say 5, 10, 15 minutes, that instance might be destroyed, because at some point AWS is going to have to reclaim the resources that we are not paying for, because we only pay for the milliseconds of execution. So you can imagine that there is this entire life cycle that always goes on. Every time there is a new event, we might spin up more instances. If there are no events for a while, the instances get destroyed automatically. If we want to go a little bit more in detail, the idea is that there are actually two components inside a Lambda, or at least two layers, if we want to describe it that way. One layer is the runtime, and another layer is the handler function, which is something we can see as our own business logic. So the runtime is just the wiring with the AWS APIs, making sure that you can get the data in the event, making sure that if you are returning a response, that the response is delivered correctly. So the idea is that the runtime, as soon as the Lambda is spun up, is going to constantly poll for new events. It's going to be checking, is there an event that I need to process? And this is basically like an HTTP call to an internal AWS API. And at some point there will be an event. That event is effectively a blob of JSON. So the runtime, what it does is going to invoke the handler function, so the actual business logic, saying run your code against this particular event. And of course, at some point, the computation is finished. We have either a response or an error, and that result is being communicated back to AWS just to make sure that AWS knows that that particular event has been processed and is not going to try to process it again. Now, why do we think that Rust is a good fit for Lambda, or at least why do I think that? The first thing is that it's a very performant language. It's a very efficient language in terms of memory consumption. And these are the two dimensions that we have for cost, right? So if we get very good performance and we can keep the memory very low, that means that we're probably going to be saving money compared to something like JavaScript, Python, Ruby, that are also languages that you can use with Lambda. It's very fast in terms of cold starts. And again, this is something that we will be paying for. So the faster it is, the less we pay. But also it's something that if we implement an API, the user is going to make a request. If there is a cold start in that moment, we are letting the user wait for a few extra milliseconds. So having very low cold starts also helps us to give a better user experience. Now, there is a very good benchmark. If you don't believe me on this, there is a link if you click in that proof that runs a bunch of lambdas with different runtimes all together in parallel. And you can see that Rust is generally the fastest one by far. Like I've seen between 10 and 20 milliseconds cold start. While if you look at JavaScript or Python, generally you are above 100 milliseconds. So there is at least a 5x improvement there. Multi-thread safety is also a great feature. You don't generally need multi-thread in Lambda, but when you need it, you can use Rust and you have that extra safety that you are not going to be doing any mistake. And the thing that I like the most, and this is my preference for Rust in general, is that you don't have null types and you have very good error primitives using the result. Great, and I invite you to read this t-shirt later. So in my experience, that leads to very few bugs because the code itself forces you to think about cases where if this value can be null, what am I doing when that value is not present? If there is an error, am I actually handling the error? I need to explicitly extract the value from the error type. So that kind of forces me to think, okay, what if I cannot get the value because I have an error? How am I handling this case? So in general, I think the Rust gives us better, well, forces us to think more about the error cases, and therefore we write better code with less bugs. Okay, let's get into the code part. Let's write our first Lambda. And just to make it a little bit easier, we're going to start with Node.js. Sorry for that. So as I said, it's a function and it's an async function. You get an event. And what you generally do, you get data from this event, you run some business logic, and at some point you have a result that you can return. Just to see a little bit of a more practical example, here we are building kind of a ping system where we want to see if a specific URL is, what's the status code basically that is returning to us. So we are basically receiving an URL as part of the event payload. We just do a fetch request, so basically doing an HTTP request to that URL. And what we do, we just return the status. So maybe something that we can use as a very simple health check, right? Maybe we can check, is this URL at 200, or maybe it's some kind of error code. Not the most amazing Lambda ever, but I hope it kind of shows what is the general structure. Get something from the event, do something useful, return some value. Now, let's say that you like all of that and you are wondering, okay, how do we do the same in Rust? And the first thing that you do, you go on AWS, you open the web console and you try to see, okay, let me select Rust from the runtimes. And then you start to see Node.js, Python, Java, .NET, Go, Ruby, custom. And it's like, where the hell is Rust, right? You are here doing a talk about Lambda and Rust, but it's not even there in the list. And to be fair, today I don't think you're going to see Go anymore as well, even though it's been there for a while. And the reason is that the way that AWS allows you to write lambdas in Rust is by using the custom runtime. And the idea is that there is a library that AWS provides that implements the runtime. And then what you do, you basically create a project using that library. And when you compile the binary, it's basically containing together the runtime plus your own code, and you can ship it as a custom runtime lambda. The reason why they do that is not necessarily public. My guess is that it's for efficiency reasons, because then you have a single binary that contains everything. So there is no message passing between maybe an independent runtime and your own code, which is what was the initial implementation in Go. And for some reason now they removed it. So that maybe proves my assumption. But the other reason is that also it's something that AWS doesn't have to maintain. They can maintain the library, but they don't have to push updates. It's on you to do the updates. So I think there is a bit of, it is probably faster, which is a good thing for us, but it's also easier for AWS to maintain. So where do we start? Now let's write lambdas in Rust, as I promised you. So there is a very good tool that is called Cargo Lambda. So we can just start by installing the tool. And this tool is a third-party CLI that extends Cargo. So you know Cargo, if you've done any Rust, is the package manager, but also a tool that allows you to create a new Lambda or any new Rust project if you want, to run it, to execute examples from repositories. It's basically the CLI that allows you to deal with Rust projects. And it can be extended. And one of the extensions is this Cargo Lambda. It's built by an AWS employee, even though I don't know if AWS would like to say that this is an official AWS project, so that could be interesting. And the cool thing is that you can also easily cross-compile for Linux ARM using Windows, Mac, or Linux. So it doesn't really matter what's your development environment. It's very easy to ship ARM Linux lambdas, which I think is the most efficient target. And the other thing is that can be integrated quite well with tools for infrastructure as code like SAM and CDK if you like to use those. Now, how do we use it? I have here a GIF. Hopefully it's going to be readable enough. But you can just say cargo lambda init. And the first thing that it's going to ask you is what kind of lambda do you want to create? Is it an HTTP function or is it something else? And here I am selecting S3. So what it does is going to say, okay, I'm going to create some boilerplate for you for an S3 event. And if we look at the boilerplate, it's going to look more or less like this. There is a bit of code, so let's try to break it down. So the first thing is that it's importing that lambda runtime as a function that we want to use, or actually it's importing a bunch of different things from this lambda runtime library. Then the other thing is that we have a main here, and this is an async main using Tokyo. Because the lambda itself can be async, so we can use futures, we can do async code, and this is why they built it this way pretty much. Then they also initialize tracing subscriber, so all the logs that you want to produce are already using tracing subscriber, which is a bit of a best practice, I guess, in Rust, because it allows you to do a bunch of things around logging, for instance, log based on levels, structured logging. You can also emit traces, connect these traces to things like OpenTelemetry. So this crate is kind of the holy grail for all things observability. And it's good that by default you get this in the standard boilerplate. And then the final thing is saying, okay, now after you did all the initialization stuff, go and run the current function that is my code, which we're going to see in a second, as a service. So this is basically that loop that I was describing before, where it's going to check, is there a new event? If there is, run this function. Is there a new event? If there is, run this function. And this is going to continue for a while until AWS is not going to decide to shut down the Lambda because maybe it's been inactive for a bit. So this is actually our main business logic. So this is, everything else is kind of boilerplate just to make sure that every time there is a new event, we are running this particular function. And you can see from the signature that it's a Lambda event, specifically an S3 event, because this is what we selected during the initialization phase. So what are we doing here? We could do whatever we want. Generally, an S3 event is because you either dropped a file into an S3 bucket, maybe you deleted something, maybe you updated a specific file. So this event tries to describe that operation that happened in an S3 bucket. Actually, AWS can batch multiple operations if you're doing very quickly. So in reality here, you might have multiple records. So we are doing a loop saying, okay, for every single record, the only thing we want to do is just print what was the operation, so event name, what was the bucket, and what was the file name. So you might have something like put example, example.txt, for instance. And then at the end, when we process all of that, we return OK. We don't really have anything to return. So in this case, we are returning the unit type as a successful result. OK, how do we run it? This is still locally. How do we test this? And Cargo Lambda is actually pretty cool because it gives us a simulator that we can run locally to test the Lambda. So we started with Cargo Lambda Watch. That creates a local server. And then here in another session, we can just call Cargo Lambda Invoke. send an example event, and we can see that basically we get some logs being printed out. So nothing mind-blowing, but just it's good to see that we have an ability to test Lambda locally, which is one of the pain points with Lambda sometimes. Now, in Node.js, you might have noticed that the Lambda signature had event and context, but here we only had an event. So what does it mean? And what is the context? So the context is something that you can use in Lambda to get information, for instance, when is the deadline for this particular execution. So if our Lambda can run for 15 minutes, maybe you want to know in your code how close are you to that deadline, and maybe do something about that if you're very close. Or maybe you can do other things. For instance, you can get the name of that Lambda function, you can get the version of the runtime. So it gives you a bunch of information about the execution context, and you can use that maybe if you need to do something specific. So how do we extrapolate the event and the context? It's a bit weird because they call this event. It's not really an event, it's more a container for both the event and the context. And they give you this particular method which allows you to destructure the two and get separated event and context. So this is going to be in our previous example specifically the S3 event, and this is going to be the context. So just something to keep in mind, because coming from Node.js or Python, initially for me at least, it was a bit confusing. Okay, now let's talk a little bit about request and response types, because one of the cool things about Rust, at least if you like that, not necessarily, is that it's a strictly typed language. So that means that for everything that you declare, you need to have a strict definition of types. So before we saw this example that our Lambda event has a generic type of S3 event, which describes that the content of this particular event is going to be all the fields and values that you can find in an S3 type of event, right? And this is what we can call the request. We also have a response here. We are saying we are not really going to have to return anything because we are just printing logs, right? But if we wanted to return something, this is the place where you can specify the type for the return type. Now the question is, what if we want to use different types? What if this is not like an S3 function, or well, it's not an S3 event, or what we want if we want to return something else, right? There are three options that I found, so I'm going to try to describe the three different options. So the first one is that if you want to use standard events, so standard AWS events, so integration with other services like API Gateway, Event Bridge, or SNS, or whatever other service you might be using to trigger your Lambda, there is a package called AWS Lambda Events, which is actually installed when you run the boilerplate. And this package contains not all, but most of the definitions that you generally have when you integrate with other AWS services. So basically, when you use this library, the only thing you need to do is select the specific type that you want to use. Now, I have here an example where, for instance, we want to process jobs from SQS. So we have jobs coming into a queue, and every time there is a new job, it might trigger a new Lambda and execute all the jobs. By the way, if you ever used SQS but not with Lambda, you know that this is actually a poll interface, and here it looks like a push interface. So it might be a little bit weird. There is actually a bit of a magic trick that AWS does, which is called Event Source Mapper, which is effectively a component that is constantly doing the polling for you and invoking the Lambdas when there are new events. So if this picture looks weird, you probably should know that it's because of that magic there. Okay, so when we want to use SQS, there is one thing that you need to be aware, that by default, when you use that init command and you select a specific event, just to keep your Lambda as small as possible and the compilation time as fast as possible, they are only going to select the specific type of event in the features list that you specified when you were creating the Lambda. So now let's say that we want to switch from S3 to SQS. We need to make sure that we update the list of features for that particular crate to say, I want to use the SQS types. And you can also say, I think, all, if you want to get all of them, but probably for most use cases, you don't need to do that. Actually, you don't need to say all. You basically just don't set these default features. So you can remove all of these default features and the feature, and that means you're going to have all the types available. But that means probably longer compilation times, probably slightly bigger binary. So let's see this event. So we want to process jobs from SQS, so from a queue. We can import all the different types that we need. Now this is a very specific event. I don't want to get too much into the details, but one of the cool things that you can do with Lambda, basically you get a batch of events. Maybe you have 20 different jobs that are coming through this event. You have your business logic. Generally you have a loop here that goes through every single item and it processes it. What happens if one of them fails? This used to be a big problem because like how do you reconcile partial success? Maybe 19 of 20 jobs succeeded, but one failed. How do you communicate back that you only want to retry one item and not all the other 19? Recently, I think this was last year, AWS introduced a feature that is called batch item failures, which is something that we can use by just saying as a response result from this Lambda, we can tell you exactly which ones failed. And then AWS is going to reschedule only the ones that failed. So basically, we don't have to worry about managing all this stuff ourselves. We just need to make sure that the Lambda returns the IDs of the jobs that failed. And now this is a bit of a contrived example, very specific to this particular task. But I just wanted to show you that everything here is typed because we can use this SQS batch response, which has batch item failures. And it's kind of easier to implement this correctly. While if you're using Python or Node.js, you're basically returning blobs of JSON, and it's on you to make sure that you are using the right naming and the right types. Okay, what's the other option? What if we want to use custom events or custom responses? Maybe we're implementing a step function. This is actually a real use case. I've done a few live streams, and there is a link I'll give you at the end. It's basically a newsletter automation that I use. So I have this newsletter called Foodstack Bulletin. It's gonna create a newsletter every week for me, and then I can manually do some tweaks and publish it. And there are a bunch of custom steps that are basically lambdas that I've written, some of them in Rust, some of them in Node.js. And you can see the live streams if you're curious to get into the details. But the idea is that, for instance, here we have this fetch issue number, which is a step that knows how to get the next number for the next issue. So every issue has a number. I don't know, this week maybe is 334. Next week needs to be 335. This lambda is responsible for fetching that information so that the next issue will have the correct issue number. So it's effectively like a progressive number. It's fetching the data from somewhere. So the idea is this one is very custom. Like there is a very specific type of input. There will be a very specific type of output, and it's not related to other AWS services. How do we define these types? And the trick is because everything is JSON behind the scenes, we can use JSON also in our Rust code. And one of the most popular ways to do JSON in Rust is to use this library called Serdi, which is a generic serialization library and has a JSON counterpart. So you need to install both the libraries. Serdi is just the generic interface, while Serdi JSON gives you the JSON serialization and deserialization. And the idea is that you can create your own structs. For instance, here, the request, I only need to know the URL of the page where I need to scrape the issue number, while the response, I'm going to be returning what is the issue number that I found in that particular page. This is a very simple example. I think in real life, you will have a lot more fields in the request and the response, but it goes to show that you can have your own custom types, and they are strictly typed. So basically what happens here is that if you receive an event that is different from the shape that you defined here, the lambda is just going to fail automatically. So that makes a little bit easier your job here to write code that is already strictly typed, and you don't have to worry about doing any extra validation or returning specific errors if it's not valid. So you can just trust, okay, this event is going to contain a URL, I can use that URL, and when I'm done, I'm going to return exactly this response. Now, the cool thing is that when you use Serdi, you have these derive macros, which basically are just going to, let's say, enhance this struct with all the code that is needed to convert this from a JSON blob into this struct if you use the serialize, or the opposite. If you serialize, it basically means take this struct in Rust and convert it to an equivalent JSON structure. Serdi has like 1 million features. This is like the most basic example. But if you have used Serdi, you can use all the features that you know and basically do JSON that way. And here there is just an example. If we run this code, the thing that I want to show you here is that you can pass your own raw JSON by using this data ASCII. And basically in this case, I'm passing a specific URL. So you don't necessarily have to take the events from a file. You can even pass raw JSON in the CLI, which sometimes is easier. Okay, what is the option tree? Let's say that we have a case where we can accept any input. Maybe we actually, by design, we want to accept a free JSON blob that can contain any field. What can we do in that case? We can still use SERDI, and SERDI has this concept of JSON value, which is like a very generic JSON value. So this value is actually an enum that can be either an object, an array, a string, a number, and all the different types that are supported in JSON. Which means that it is on you then to do all this work and make sure that you check, okay, give me the payload. Let's try to read it as an object. This can fail. So we need, here I'm unwrapping just for simplicity, which you shouldn't really do. But this gives you the idea that you need to handle all the possible error cases in trying to read the specific fields that you need to read. So it is convenient that we can do that, but generally brings you a lot of work that maybe you don't want to do. So when you can use strict types, I think it's generally easier. And the other thing is, what if you want to return a generic JSON blob? Maybe you don't want to define your own type because either it's something simple or maybe it's something that can change a lot depending on the different code paths. Then you can use this macro, JSON exclamation mark, and pretty much then you can just write JSON in Rust. And SERDI is going to do all the work of converting that to a proper JSON string. Now let's talk about HTTP, because this is probably the most common use case, at least as far as I've seen. You can build APIs with Lambda and API Gateway. So how do we define HTTP events, and what do we need to return when we run an HTTP event? And this is something that we can just do here when we bootstrap our code. If you select, is this an HTTP function? You can say yes, and it's going to create a slightly different boilerplate, which is more suitable for HTTP lambdas. And that code is going to look like this. So basically, rather than using the runtime, it's going to use this lambda HTTP, which is a slightly higher level abstraction. And then that HTTP gives us a request object, and the result is a response with a specific body. And for instance, this is the classic hello world that you get in any web framework. You can receive a query string parameter that says the name, and the endpoint just returns hello for that name. Or if you're not providing the name, it's going to say hello world as a default. So here what we are doing, we are saying this event is going to represent an HTTP request. So we can read things like the query string parameter, the body, the headers. In this particular case, we are only reading the query string parameters and looking for a parameter called name. And if it's not there, we are going to default to world. Then we create our message. So this is what we want to return to the user. But also we need to create an HTTP response. And we know HTTP also has a very specific format that we need to respect. Furthermore, in Lambda, there is a very specific integration, which is called Lambda API proxy, I think, which defines what is the JSON object that you need to return in order to describe an HTTP response. But in this case, because we are using Rust and we are using this typing system provided by Lambda HTTP, we have this nice builder pattern that makes sure that we provide all the different fields that are needed. So we can specify the status, we can specify additional headers, we can define the body, and finally, if there is an error, we can describe how to map that error to a specific response. And by the way, all of this behind the scenes is still going to be JSON. So the runtime is still going to read and send JSON back to AWS. So you can see those are just nice abstractions that you can use to make your life easier and make sure you don't do any error in reading the JSON requests or returning a very specific JSON response. Now, getting close to the end, how do we build and deploy all of this stuff, right? The cool thing is that Cargo Lambda gives you also the ability to build, but also to deploy Lambdas. And these are the two commands that you need to use: Cargo Lambda build release and Cargo Lambda deploy. And what it's going to do, actually, I have a GIF here. So if we run Cargo Lambda deploy, you can see on the file tree there on the right, that it creates in the target folder a release folder, and inside that release, we'll see in a second after it finishes to compile that there will be a specific binary which represents our custom runtime together with our custom code. Now this is Rust, so the first time you compile, you might go and take a coffee, but after that it's generally a bit faster. So you can see here that there is a release, and inside we have this bootstrap. Then when we run cargo lambda release, what happens is that basically we need to zip that file and just send it to AWS. And this is literally, again, our custom runtime plus our specific business logic, which is going to be used as a Lambda function. Okay, then next slide, please. What happens if we go in the AWS console and try to check out what is the result of that deployment? Well, first of all, because Lambda gives you, Rust gives you a binary, you are not going to be really seeing anything useful there unless you can read ELF code yourself, which I don't think so, because also it's not really giving you clear binary definition there. But anyway, this is basically the binary that contains all the runtime plus your own code. And AWS knows exactly how to interact with this one. One of the problems that there is there, outside the fact that you cannot change the code from this editor, you need to redeploy yourself, is that there is no trigger configured. So we just built an HTTP Lambda, but this is not really creating any API gateway. It's not connecting this Lambda to basically an HTTP trigger. So this is something we will need to do ourselves, and it might be error prone. And how do you do it? Do you do it manually or do you do it in some other way, right? And the answer to that is that you need to do infrastructure as code. This is kind of a best practice in the cloud. And I have an example with SAM. SAM is not the only tool. You can use CDK, you can use CloudFormation, you can use Terraform, you can use Pulumi. There are like so many of these tools. But it's just the one that I found the easier to showcase, especially in combination with Cargo Lambda. So it's an infrastructure as code tool. It uses YAML. And I think it's great when you have to do a bit more than just a single Lambda function. Maybe you need to create buckets. Maybe you need to create API gateways. Maybe you need to create specific policies. You can define everything in one or more YAML files. And then when you say deploy, you can be sure that all the resources are created consistently. And you can deploy the same thing in dev, QA, production, other accounts in other regions, and so on. I have a very quick example here that just shows that, for instance, here we define all the resources, and there is a Lambda function. In this case, it's a Node.js one, but also there is an S3 bucket. So when we deploy this code, it's going to create both, and it's also going to link this Lambda, creating an event listener that listens for events in this S3 bucket. So you can even create references, and AWS is going to make sure that this bucket is created first, gets the ARN of that bucket, then creates this Lambda and configures the triggers correctly, referencing that bucket. So you can immediately see that when you start to have dependencies between resources, if you don't use infrastructure as code, you make your life much harder. Now, the cool thing is that SAM is already integrated with Cargo Lambda. It's a beta feature, so you might have to enable it explicitly, at least in the short future. I think it's close to become a non-beta feature because it's been beta for a while. But today, you can still use it, and I've seen it working quite reliably. So the idea is that you define all the infrastructure as code with SAM, which is built to do that. But then when you want to build and run your Lambda locally or deploy to AWS, use Cargo Lambda to do all the packaging and all the local simulation. And it can even simulate API gateway locally. You have something similar also for CDK. If you're using CDK, I haven't tried it, but there is a repository there that you can try if you are more into CDK. Now, this is just an example. So basically here we have our own Lambda, the one that we saw before, that HTTP endpoint. But we want to make sure that we also provision an API gateway and that this Lambda is going to listen to the / endpoint for GET requests and is going to trigger our business logic. So this is all the YAML that we need to write for SAM. But we also need to write a bit of configuration which makes sure that we enable the beta features. Oh, I actually had queues there. So this is saying when you build, use Rust Cargo Lambda. This is saying you have to use the kind of the custom runtime. This is creating the event that only listens to GET requests on the slash endpoint. And finally, we are enabling the beta features. So basically, every time it's not asking us, do you want to use beta features, yes or no? Now, how do you build and run it locally? Because we have an API, we want to test it using HTTP. We don't want to write JSON, I guess, to test an HTTP endpoint. Can we do that locally before we deploy to production? And some allows you to do that. So we can use some build, some local start API, which starts a local simulation for API gateway. And then when we are ready to deploy, we just say some deploy, and it's going to package everything and deploy it correctly. Even if you have multiple lambdas in the same project, it's going to compile all of them and deploy all of them together. And I have here just a last example. So here I'm using some build. Then I'm going to be running the some local start API to start API gateway. So this is creating a local web server, and at this point I can just use curl to call that API. So here I'm passing name crabs, and it takes a while because at this point it's building the Lambda for the first time, which is not what's going to happen in production. This is just a local simulation. And at some point it's going to say, hello crab, this is your AWS HTTP request. Then I do another request without the query string parameter, and it's just saying hello world. And finally, if I say name Dublin, it's going to say hello Dublin. So this is kind of proving that our API works locally. Then we can deploy it. And it's again, some build and some deploy. It's going to do its own thing. It's going to show us the list of resources that are actually, it's going to upload the code to S3 first. And then it's going to create a change set, which is basically a concept that says, what are the things that are going to be changing if you deploy now? And it's basically saying, okay, you're going to create a new Lambda, you're going to create some permissions, you're going to create an API gateway, bunch of different things. If we confirm that, it's going to start the deployment. And at some point, we have our Lambda in AWS that we can use. Now, just some closing notes. I think Lambda is great. Most of the time, for many use cases, you can use it reliably, and it's a good solution. Writing Lambdas in Rust is not something that you will see a lot in real life, I think, because it's just very new. But I have seen that all the tooling is already there. You can test locally. You have all these libraries that can help you. And it can be very fun and cost efficient to write Lambdas in Rust. So my advice is, if you like Rust, if you're using Rust already and you have to write a Lambda, why not doing that? Or an even better use case is if you already have Lambdas running in production and you know that those Lambdas are getting thousands of executions per minute, per day. You have very hot Lambdas that are running all the time, and maybe they're written in Python, in Node.js, in Ruby, which are generally more expensive languages. You might have a business case right there. Just rewrite that one Lambda function. And generally, Lambda functions are very self-contained, so you don't have to rewrite the entire project. It's just one function. So I think this is a very good first use case if you want to try to introduce Rust into your own company. So go have fun and share your learnings. And yeah, thankfully you appreciated this talk. I also have one bonus slide, which is basically a full example that I built using SAM and Lambda in Rust. It also uses Event Bridge, uses SNS. So it's a bit of a more complete example if you want something a little bit more realistic, I guess. So I'll leave you with that. And I guess now, I don't know if we have times for questions or...
Yeah.
Cool.
Question. If you had multiple input sources, you want to be able to take the same type of data from S3 or over HTTP, what pattern would you use there? Would you pass it on to another queue from a pre-processed Lambda so that you're not maintaining the code in multiple spots?
Yeah, I guess one way could be there are probably different solutions, but if we just want to stick up to think about how do you write Lambda code in Rust that can be flexible to handle multiple types of events, what I will probably do is, as a signature of your Lambda function, you accept a generic JSON value, and then using serd you can say try to cast this JSON value to the specific type. If it fails, you try the other one. If it fails all of them, maybe you return an error saying this is not an event, I understand. That could be one way. Otherwise, there are probably a bit more complicated patterns if you want to kind of offload all that work to the infrastructure. You can probably use Event Bridge and Event Bridge pipes to do some kind of manipulation. Don't know how flexible that could be. Probably you can do basic transformations. So depending really how much flexibility you need, you might be able to offload something to AWS. Any other question?
There's no questions coming in. We got a brilliant thanks from the live.
Oh, we have maybe a question there.
Quick question. I've seen that it's based on Tokyo as a framework.
Mm-hmm.
So it's async since the beginning of
Yes.
the platform. I don't know if it makes much sense in lambdas, but would it be okay to have like multiple spawn multiple Tokyo threads in the same lambda context? I don't know if that's
Mhm.
feasible or.
I think it is feasible. It might make sense, for instance, I don't know, let's say that let's go back to our first example where you have a URL and you want to get the status code, right? I think let's say that you can get an array of URLs as your event input. So maybe you want to scrape all of them as much concurrently as possible. In that case, you can definitely use the async runtime, spawn multiple async tasks, do a request to all of them, collect all the status codes, and then create a single response. That should definitely work. Not something that I have tried, but I mean, it's Tokyo, so you can do everything you can do with Tokyo. And just because that's a good cue, something that I wanted to explore, but then I noticed that the presentation was getting too long, is the fact that the Lambda function itself is actually a Tokyo service. So it's actually implementing the service trait, which if it's something that you use, you probably know that brings an entire like middleware framework that you can use. So you can basically say, I don't know, you can add delays, you can add all sorts of behaviors just with an annotation on top of your function. And this is something that for me is very cool because in Node.js, I implemented a framework called MIDI, which does all of that. And it's an external thing that you need to install and use it and maintain as a community. And it's very cool that this is already built in the Rust runtime.
Yeah, I noticed that there was a bit of like boilerplate with because there's the Tokyo main function that essentially runs once because it's a process that runs once in the cold start in the micro VM.
Yeah.
But you still have to write that out, whereas you wouldn't have to do it in like Node.js, you just export the function. It sounds like it'd be a very good use case to just write a macro around the function handler to do that. I guess that's the reason why they haven't done that, I assume.
That's a good point. I think it's definitely feasible. Like I don't see any reason why you couldn't do that. But on the other end, if you use Cargo Lambda, which probably most people would use because it just makes your life easy, when you do Cargo Lambda init, it creates that code for you. So it's generally something you don't have to think too much about because it's probably going to be part of your initial scaffolding.
Yeah, okay. Thanks.
But yeah, maybe an idea for a contribution to the runtime. I think it might make things easier for people that want to do that part manually for sure.
Yeah, I'll look it up, and it's an easy enough idea that I'm pretty sure they already discarded for some reason. I'll figure it out.
Could be, yeah. But you can always open an issue and see what they have to say. Okay. Yeah.
At the beginning, you mentioned that some of the limitation was that there was some limit on the request size,
Mm-hmm.
and then I think you also mentioned that AWS sometimes batches the request.
Mm-hmm.
So I was wondering if that request size limit worked at like a batch level or at a single request level.
Yeah, no, in AWS, when it comes to limits, it's a bit crazy. Like you really need to read the fine print and figure out all the limits. Because for instance, I don't know, another case could be when we saw the example where we were integrating SQS with Lambda and you receive a batch of events. Also, SQS has a limit on the payload size. I think the limit is actually bigger than the one you can do with Lambda, especially because it might batch multiple events. I don't know if they do anything smart on their end to try to make sure that the size of the payload you get in Lambda is actually constrained within the boundaries of that Lambda. I think in that particular case, the limit is 2 megabytes. So probably you have enough space to describe a few jobs for most use cases. But it's definitely something to be aware, especially if you expect that you'll need to send a lot of data to the Lambda. You might hit those limits. So in those cases, you need to be careful. Generally, the input is fairly limited. Even an HTTP request, if the body of the request is not huge, should fit into the few megabytes that you get of payload size. I think the main problem is when you want to implement something like an upload or a download where you could have multiple megabytes of incoming or outgoing data. In those cases, you might want to use something like S3 pre-signed URLs or something like that. Yeah.
You mentioned the idea of replacing maybe like slow Python lambdas with Rust.
Mm-hmm.
How do you make sure there are like no regressions? Do you know like a good like a lambda testing framework?
That's a good question. Yeah, I mean, the good thing about Rust is that the unit testing framework is built in, right? So you can easily write tests that way. There are also more advanced crates that you can install if you want a more kind of fully fleshed out test framework. But I don't think it's too much different than writing tests in Python or, I don't know, Java or any other language, with the exception that it's a typed language. So when you have to mock or do very dynamic stuff, it's not as easy as it would be in Python or JavaScript. So you need to know exactly how to do, I don't know, dependency injection and all the kind of techniques that might help you to make your code more testable. But besides all of that, you still have a framework for writing tests. You can write unit tests. You can do all the testing. I guess it's more of a business question. How do you make sure that you replicate the same tests into the new environment? So do you already have unit tests in Python? Can you easily port them over? Like, is the input and the output very clear? So I think it's more of a business question at that point to how much can you raise the confidence that you don't have regression depends on the quality of your actual code base and how easy it is to port the same quality to the Rust Lambda.
Yeah, talking about limitations, is there any limitation over the artifact, the release binary that we upload to AWS?
Oh yeah, good question. I think the default is 50 megabytes. I might be wrong. There is a limitation.
56 megabytes for your
Okay.
high, but you can deploy it as a CI image, basically
Yeah.
Docker image, and it's up to 10 gigabytes.
Yeah.
And like it's
Yeah.
enough for everyone.
It's probably a bit trickier to package the Lambda, especially if you now that I've shown all these tools, I don't think that they support Docker. Maybe I'm wrong, but there is an option where you can package it as a Docker image, as you said. And I've seen that used only once in my career when they were trying to ship an entire ML model inside the Lambda just to do inference. So then you need multiple gigabytes, but that's the solution. So there is a specific solution for that one.
I might have missed it. Did you say the keep alive time was arbitrary? It just depends on AWS's load?
Yeah, it's not officially published. I think I've seen a research years ago of somebody trying different things and trying to observe when the Lambda was being shut down by basically looking at, if I do another request, is it going to be a cold start or not? And they observed that it was very variable between 5 minutes and 15 minutes. So I think it's rarely going to go above 15 minutes. Most likely it's going to be within 5 minutes. Okay. Any more questions?
Yeah, with no questions online here.
Cool.
Just probably one corner question, one
Mhm.
comment. You mentioned that for us to have these strongly typed bindings for different events, and
Mhm.
Node.js and Python will probably miss them. And as far as they know, the Power Tools libraries
Oh yeah, yeah.
for Lambda, and they have not only bindings but some like framework patterns, best practices, how to do idempotency and things like
Mhm.
that, and they like building blocks and you can use. And I think it's available for Python, .NET,
Yeah,
probably
Node.js.
Java,
Yeah.
and Golang runtime. It has bindings as well
Mhm.
on GitHub, and you can do exactly the same.
Yeah, I think, I guess the difference is there, for instance, if you use Python, you have Python typings,
Yeah.
which is not necessarily enforced at
Mhm.
runtime. So it's
Sure.
on you to make sure you still run the validation and handle potential errors. So, but it's definitely a good point. So if you're writing lambdas in other languages, check out Power Tools, because so much good stuff that is going to make your life easier anyway. Thank you for that one. Okay, should we call it?
Yeah, I think
Yeah.